Have you ever wondered what your voice actually looks like as data? Or how a digital song is even stored on your phone? Well, it all comes down to something called discrete time signals. These are the fundamental building blocks, the actual language of all digital signal processing. So let's get right into it and see how this all works.
So here's our game plan. We're going to start with the big picture. Then we'll break down the 4 essential signals you absolutely need to know. After that, we'll look at the tools we use to tweak and combine them, walk through a solid example, and see how this stuff actually shows up in the real world. And of course, we'll wrap it all up with a handy summary.
All right, so let's kick things off with the core idea. I want you to think of any piece of complex digital information, like a sound or an image, as a big, complicated Lego structure. To understand the whole thing, you've got to start with the individual bricks it's made from.
Take a look at this audio waveform. At first glance, it looks pretty complex, maybe even a little chaotic, right? But what if I told you that this entire thing is just a combination of a few surprisingly simple fundamental signals? And that, right there, is the secret sauce of digital signal processing. It's all about understanding how to build and break down any complex signal from these basic pieces.
And that leads us perfectly to our 4 fundamental signals. I like to call these the atoms of the digital world. Seriously, if you can get a good handle on these 4, you're well on your way to mastering the basics of pretty much all digital signals. First up is the unit impulse, which we write as delta of n. The definition couldn't be simpler. It's a signal that has a value of 1 right at time 0, and it's 0 everywhere else. Think of it as the shortest possible event you can imagine, like a single instantaneous blip. It's so important because it lets us test out systems by seeing how they react to this one tiny input.
And here's what it looks like. It's literally just a single spike at n equals 0. It might not look like much, but trust me, this simple little signal is one of the most powerful tools we have for figuring out how complex systems work. Okay, next up we have the unit step, or U of n. The best way to think about this one is like flipping on a light switch. The signal is off, it has a value of 0, for all the negative time leading up to 0. Then, right at time 0, it turns on to a value of 1, and it just stays on forever.
You can see it really clearly here. It's just 0, 0, 0, and then BAM! At n equals 0, it jumps up to 1 and stays there. This makes it the perfect model for anything that starts at a specific moment in time and then just keeps going.
Our third atom is the real exponential. This is basically a sequence where to get the next sample, you just multiply the current one by some constant number a. Now, here's where it gets interesting. The behavior of the whole signal completely changes depending on what that value of a is. For instance, if a is a number between 0 and 1, say 0.8, the signal gets smaller and smaller over time. It decays. And you see this shape everywhere in the real world. It's the fading echo after a loud clap. It's a hot cup of coffee cooling down. It's even radioactive decay.
And finally, we have the sinusoid. This one probably looks familiar to you. It's that classic, perfect, repeating wave. The equation here just tells us its height, or amplitude A, how fast it oscillates, its frequency, omega, and where it starts, its phase, phi. This is the very essence of anything that vibrates or oscillates.
And visually, it's exactly what you'd expect. A beautiful, smooth wave, just sampled at these discrete points in time. Everything from the pure sound of a musical note to the AC power coming out of your wall sockets is built on this fundamental shape.
Okay, so now we have our 4 atoms, our 4 basic signals. But that's only half the story. Now we need a toolkit to actually build things with them. These are the basic operations that let us modify our building blocks and combine them into something way more complex.
For this explainer, we're going to focus on 2 of the big ones. First is time shifting, which lets us move a signal forward or backward in time. And second is amplitude scaling, which basically just makes a signal louder or quieter. Let's see them in action.
Let's start with the time shift. On the left, you see our original signal. Now on the right, we have x of n-3. And look, every single sample has just been pushed 3 spots over to the right. This is a key thing to remember. A minus sign inside the brackets means a delay, a shift to the right. And now for scaling. Again, the original is on the left. On the right, we have 2 times x of n. You can see it's the exact same shape, but now every single sample is twice as tall. We've amplified the signal. And of course, if that number was less than 1, say 0.5, we'd be squishing it down, making it quieter.
So, we've got our atoms, and we've got our tools. It's time to put it all together. Let's walk through a quick example. This is a classic kind of problem you will definitely see on an exam, so it's good practice.
So here's our challenge. We're given some signal, x of n,
And we need to create and graph a new signal, y of n, which is defined as 2 times x of n minus 2. So you can see this combines both of the operations we just talked about.
Now, the key here is to do these operations in the right order. A good rule of thumb is to work from the inside out. So first, we deal with what's inside the parentheses, the time shift. We take our original signal and delay it by 2 samples. Then, we apply what's outside, the amplitude scaling. We take that new, shifted signal and double the height of every sample.
And voila! Here's the final result. You can see the original signal there for comparison. Our new signal, y of n, is clearly shifted 2 spots to the right, and every one of its samples is exactly twice as high. We've successfully built our new signal step by step.
So, why does any of this theory actually matter? Well, because this process of combining and manipulating simple signals is exactly how we describe and create every single complex signal in our digital world. We're finally moving from our simple atoms to building real, complex molecules.
And this is the big payoff, the main idea I want you to take away. Remember that complex audio waveform from the beginning? It's really just a massive sum of our basic signals, mostly sinusoids and impulses, that have all been shifted, scaled, and added on top of each other. This idea is called superposition, and it's the absolute heart of DSP. It means we can break any signal down to analyze it, or we can build any signal we can imagine from scratch.
Okay, let's wrap this up with a quick summary. You can think of this next slide as your personal cheat sheet for this whole topic. It's got all the key ideas and notations we covered in one place.
And here it is. We've got our key building blocks, the impulse, this step, and the exponential. And we have the proper notation for our essential tools, the time shift and amplitude scaling. Honestly, having this table handy will be a huge help when you're solving problems.
So, we've covered the essential building blocks. You now have the fundamental toolkit to understand, and even speak, the language that powers our entire digital world. So the question I'll leave you with is this. Now that you have the tools, what's the first complex signal you'd want to try and build, or take apart?